Welcome back, and today we're going to talk about counting and probability. So up until this point we've talked about the different ways of getting probability, the definitions, the empirical definition, the theoretical definition, and at this point we've always known the sample space. We knew what numbers to divide, right? As long as you know what number goes on top and what number goes on the bottom, you just divide, and it was easy to get those numbers. Well, what happens if you can't get those numbers, or it's almost impossible, practically impossible, to get those answers by using the methods that we've done, like going out to the sample space, right? It's one thing to say, okay, well, how many possible outcomes are there on 3 flips of a coin, right? I can either get heads, 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 tails, heads, tails, heads, and so on and so forth, right? And we can write out the 8 possible outcomes, right? And so we've been doing those sorts of things, and then we can apply the definition of probability to those cases. Or we've been given a contingency table, or we've been given data, and we can do the relative frequency, right? We can get those numbers, okay? But what if the possible outcomes for an event are in the millions, okay? Or in the tens of thousands even, or hundreds, right? Even in the 50s or 60s, right? We're not going to want to write out all those and figure out by using the methods we have. Well, that's where counting principles come in. So we're going to use counting principles to find out what number goes on top and what number goes on the bottom. And so that's what this section is going to be all about, counting principles and probability. Okay, and so this will be the last section, and so now what we're going to do is put it all together. Okay, so now let's start with a couple of ideas. Okay, one, couple of questions you want to ask yourselves throughout this whole process, and I've said this in class, but I'm going to start with these questions. The one question that you want to say is, does order matter in the problem? Okay, that's going to be one of the key questions we're going to ask. Does order matter? Okay, that's going to determine how we approach the problem. The other question is that we're going to ask is, are we using replacement or not? Are we doing it with replacement or without replacement? That's going to be another key question. Okay, and because it's going to that's going to bring up the question of independence that we talked about before. Okay, so again, the questions we ask ourselves: does order matter? And are we doing it with replacement or not? Okay, hope that makes sense. So now, let's start with the fundamental counting principle. This is where the rubber meets the road. So everything's going to start with the fundamental counting principle. Okay, and what I'll abbreviate it as FCP. Okay, so what does the fundamental counting principle tell us? Well, the fundamental counting principle tells us if we have a certain number of steps in a process and they are distinct, and if there are different ways of doing each step, so distinct ways of doing each step, okay? Well, then the question then says, hey, how many different ways can I complete the process? And so the fundamental counting principle basically says this: if I have n ways of completing the first step, right? And I have n sub 2 ways of completing the second step. And then I have n sub k ways of doing the kth step, right? So these are all distinct steps, and there's n ways of doing the first one, n ways of doing the second step all the way down to n sub k ways of doing the kth step. Well, how many different ways can I complete this process? Well, the fundamental accounting principle just says, well, you take the number of ways of doing the first step, the number of ways of doing the second step, all the way to the number of ways of doing the last step or the kth step, and multiply them all together. So we would just take these and multiply them all together, and the result is going to be the total number of distinct ways of completing the process, the steps. Okay, that's the fundamental accounting principle. Okay, so now let me show you another example that you may be more accustomed to. So let's say you're at a restaurant and they have a special where, hey, you can create your own meal. Okay, so let's say you can, based on for $20, let's say for $20, you can choose one appetizer, one entree, and one dessert. Okay, and so let's say this is a dinner for two. $20, dinner for two. Okay, and you could choose one entree or one appetizer, right? So here's your different categories. So you have one appetizer, one entree, and you can choose one dessert. Okay? So, well, how many appetizers are there? Well, let's say you have seven appetizers to choose from. Okay? And let's say there are 9 entrees to choose from. And then on the dessert menu, let's say there are 6 desserts you could choose from. So the question is how many different meals can I create? Well, the fundamental accounting principle says just multiply all the numbers together. So you take all the different ways of choosing an appetizer times all the different ways of choosing one entree times the number of ways of choosing one dessert. And so how many different meals are there that I can get for $20 for 2 people? Well, it's going to be 7 times 9 times 6. So what does that give you? Well, it's going to be $300, and so 42. $378. Okay, so that means I have a total of 378 possible meals I could create. Okay, that's the fundamental accounting principle in action. Okay, so if I have distinct categories and I have different ways of doing each one of those, or I have distinct objects, right? Here's another way of looking at it. If I have distinct categories and I have N1 distinct objects in this category, and I have N2 distinct objects in this category, and N3 distinct objects in this category, then I can just multiply it across. Okay, and that's what I did. Okay, so that's the fundamental accounting principle. So now, let's look at some examples here. Let me see here. Okay, so let's say I have a license plate. Okay? And I want to know all possible license plates I could get. Now here's the thing, here's the conditions. Okay, so it's a 7-character license plate. So it's a particular state. So it's a 7-character license plate. The first 3 characters are letters. The second 4 characters, the last 4 characters are numbers. So digits 0 through 9. Okay. Now, one of the things that you want to notice about the counting principle is that order matters in this case. So whenever we're talking about the counting principle, it's always order matters. Okay, that's one of the assumptions. It's an ordered arrangement of objects. So how many distinct ordered arrangements of objects can I get? That's what the counting principle gives us. Okay, so that's why it's important to think about it in sequence of steps, because the steps matter. Okay, so now here's the license plate. So order matters in a license plate, right? So here are the 7 characters. Okay, so we know the first 3 are going to be letters. And the next 4 are going to be 0 through 9. Okay? So now, if I allow for repeated characters, so here's the other thing, I'm going to repeats, right? So I'm allowing for repeats. If I allow for repeats, well, if the first 3 have to be letters, and I can repeat letters, so that means I can have A, B, 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 and so on. If that's the case, then how many letters do I get to choose from for the first position of the license plate? Okay, it's going to be 26. And then what's going to be the second number? Well, it's also going to be 26 because I can repeat the number, repeat the letters. And then finally, the third one will also be repeat. Okay, 26. Now if I go to the last 4, well, how many digits do I have to choose from for the next position? Now we're talking about numbers now. It's going to be 10 because I have 0 through 9. So I have 10 here. And if I allow for repeats, then I get 10 all the way down because I can have 9999, 0000, and so on. So now I got 10, 10, and 10. So now, all I have to do is use the fundamental counting principle and multiply them all together. So just visualize and just add multiplication signs here. And so what happens if I multiply across? Well, how many different license plates do I get? I get $175,560,000. Oh, excuse me. 760. 760,000. Okay. That's how many possible license plates there are if I allow for repeats. Okay. So now the next question is what about if I don't want repeats? How many different license plates are there if I don't allow for any repeated characters? Which means once A is used, it's no longer available. Or once I use the digit 9, it's no longer available. Well, this is how you would do it, right? So now what I'm going to do is we're going to say no repeats. And I'm going to have my dashes, my position holders, right? So now again, these are the letters. And these are the digits 0 through 9. Now, once I choose my first letter, first of all, how many letters do I get to choose from for the first one? Well, I get all 26 letters, right? Now, once I choose my letter, whatever it is, let's say I choose A. How many letters do I have to choose from now for the second one? Well, if I'm not going to repeat, that means it's off the table. I'm not, you could think it's no longer available, right? So it's crossed off. So that means I only have 25 for the second one. And then for the last one, I only have 24, right? So I hope that makes sense, because as I'm choosing, it's reducing the number of available letters to me, right? So I had 26 available to me for my first choice. Then I only have 25 available to me for my second choice, and so on, okay? Now I'm at the digits 0 through 9. So now the first number that I choose, I have 10 to choose from, right? And then after I choose one, I only have 9 for the next one, 8, and then 7 for the last one, okay? And then use the fundamental counting principle. So I'm going to multiply all of these together. And so this will give me the total number of license plates that I can have that don't have any repeats, okay? And again, order matters, right? This is under the assumption that order matters, okay? So now, how many outcomes do I get for this one? Considerably less. So it's going to be 78,624,000, okay? So now that's the total number of license plates that I can have that don't have repeats. So now the question then I could ask is, what's the probability that if I randomly select one license plate, that license plate has no repeats? Well, what do I need to know? I need to know how many possible license plates there are, right? I need to know the sample space, the sample size, right? And then I also need to know how many outcomes there are that give me a license plate that has no repeats. Well, do we know those numbers? Yes. We know that this is the total number of possible license plates we can have, allowing for repeats. And then this is the total number of license plates we can have that don't allow for repeats. And so all I need to do is to find the probability, divide those two numbers. So, if I want the probability of no repeated characters, no repeats, right? So having a license plate of no repeats, it's going to be 78 million, oops, $624,000 divided by 175,760,000. And so what's the probability of that? Well, let's find out. .447. And that's it. So there's an example of where we used the fundamental counting principle to figure out what number goes on top, what number goes on the bottom in order to calculate a probability. Okay? And that's really the way you would attack it. So if I was asked, let's say I didn't know this, right? Let's say I know the situation. I know what state it is. I know that, hey, this is the way you do the license plates. And so if I was asked, hey, what's the probability that I get a license plate with no repeats? Well, I would need to know how many ways I can get a license plate with no repeats. And then I would also need to find out, well, how many different license plates are possible? Well, that would allow for repeats. Well, then I would just go through and use the fundamental counting principle. Okay? So, I hope that makes sense. Now, let's see here. I'm trying to think. Is that right? Okay, here we go. How about this? What about the probability of having at least one license plate with a repeat? So, well, that would be pretty hard to do directly, because that would mean that we would have to consider 1 repeat, 2 repeats, 3 repeats, all the way up to 7 repeats. I don't want to do that many calculations. It would be tedious, but there's an easier way. Let's use the complement rule. So remember, at least 1. The complement to at least 1 is none. So if we want the probability of at least 1 repeat, right? Oops. Then that's the same as just 1 minus the probability of no repeats, right? Well, we know that answer. We just got it. So here we could just use the complement rule and just do 1 minus 0.447, and so we know the answer is 0.553, and we're done. Okay. So that's it. That's it for that one. So let's do another one. Let's say let's do Social Security numbers. Let's do Social Security numbers. Okay. Let's assume repeats. Well, how many digits is a Social Security number? Well, let's do this. Ready? We have 1, 2, 3, dash, 1, 2, dash, 1, 2, 3, 4, right? So we've got what? 9 digits, right? So now, let's assume that we can repeat numbers, right? You can have a Social Security number of 999, okay? Well, how many possible Social Security numbers are there? Well, if I'm allowing for repeats, then how many digits do I have for every single one of these? 10, right? So this will be 10, 10, 10, 10, 10, 10, 10, 10, and 10. And so then the fundamental accounting principle just says, just multiply. And so what is this? Well, the answer's easy. Just count the tens, right? I have 9 tens, so it'll be 1 followed by 9 zeros. So how many possible Social Security numbers are there? 1 billion. Okay? So I think we have plenty of numbers to choose from. Okay? So now, how many Social Security numbers are there that don't have repeats? Now what do we do? Okay? Well, let's do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, how does that work? Well, if we're not doing repeats, that means once we choose a number, it's off the table. So that means we have 10 for this one, 9, 8, 7, 6, 5, 4, 3, 2, right? And so we're going to multiply all those together, and what do we get? Well, let's find out. We get 3,628,800. $3,628,800. So let me ask the question again. what is the probability that if I randomly select someone in the United States, randomly select a random person, what's the probability that that random person will have a social security number that has no repeated digits? Well, we're going to take our definition of probability, right? And we're going to take the number of social security numbers possible that give us no repeats. That's this number, 3,628,800, divided by the total number of possible social security numbers, which is 1 billion, and divide them. And so we get 0.004. So very, very small possible probability. So not very likely that we're going to randomly choose an individual that has a social security number that does not have any repeated digits. In fact, mine has repeated digits, and probably most of you that are listening has repeated digits. Okay? So now, what about the probability of having at least one repeated digit? Well, we're going to use the complement rule, right? Anytime you hear the phrase at least one, you should be thinking the complement rule. So if I want the probability of having a social security number of at least one repeated digit, then I'm going to use the complement rule, which is 1 minus the probability of no repeated character or digits. And so we already know that. That's 0.004. So that's going to be 1 minus 0.004, which is going to give us 0.996. Okay? And that's it. So again, we're using the complement rule whenever we have at least one. Okay, so now, let's see. Now, let's look at a 5-digit identification number for employees. Or you know what? Let me see here. Let me see here. Yeah, let's do that one. So here we go. We're going to use a 5-digit identification number for employees, okay? So in this one here, the way it works is, let's say, it's a 5-digit employee identification number, okay? And the first digit has to be a 9. Okay? In fact, it doesn't even matter. You could use any, like a letter. I could say, let's say the first character has to be a W and it's followed by 4 numbers. So how many choices do we get whether we say, okay, the first one's going to be a 9 or a W? Okay? We only get one choice, right? So let's say the first one has to be a W. Well, we only get one choice. So that's just one here, right? Oh, let's do it this way. let's say the first one has to be a W, so we only get one choice. It has to be a W. That's it. Okay? Now, what about if the rest of these are the digits 0 through 9? Now, what are the total possible number of, let's even make it student IDs. Okay? I know there's more digits to a student ID than that, but let's just say it's student ID and it starts with a W. Okay? Well, how many different student IDs can I get? Well, if I allow for repeats, I could have 0000, 9999, right? So that means I have 10 for this one, 10 for this one, 10, and 10. So how many possible student IDs can I come up with? Well, it's going to be oops, 10,000. Right? Now again, let's say I ask the question, what about student IDs that don't have any repeated characters? Okay, well, that's going to be the same thing, except now what are we going to have? Well, the first character still has to be a W, so that's not going to change. So this will still be a W, which means we only get one choice. Now here, how is this going to work out? Well, the first one we're going to have 10, right? 0 through 9. Then we're going to have 9, 8, and then 7. And then if we multiply those together, what do we get? $5,040. And so again, what's the probability that if I randomly selected a student, that they would have a student ID with no repeated characters? Well, we're just going to divide these two numbers, right? So the probability of no repeats, oops, is just 5,040, oops, over 10,000. And so what's that probability? .504. Oh, I should have known that. You just move the decimal point over 4 spots. So 1, 2, 3, 4. So .504. Okay? So now it's that easy. And then the rest of the questions, same idea. What's the probability of having at least one repeat? You would just use the complement rule. Okay? So now let's talk about some other mathematical functions that we're going to use. So let's talk about some symbols. The first symbol I want to talk about is the factorial symbol. So if we have n positive integers, so if we take the first n product of integers, positive integers, then that's going to be what we call a factorial. Okay? And the symbol for a factorial is the upside down, is the exclamation point. So the exclamation point is a factorial symbol. So what does n factorial? So for any positive integer, n factorial means I'm going to take n times every integer less than n and multiply it together. Okay? So that means I'm going to take n times n minus 1 times n minus 2 all the way to n minus n plus 1 to 1. Oops, hold on. That's going to be 2. Now we just do it this way. Okay, so that's what it means to be n factorial. Now, here's a couple of things that we could do. Note that we can rewrite n factorial in a lot of different ways. We could write this as also equal to n times n minus 1 factorial. okay? Or n times n minus 1 times n minus 2 factorial, okay? So let's put some numbers to it. So if I want 9 factorial, well, that's going to be equal to 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. Or I could write it as 9 times 8 factorial. Same thing, right? Or I could write it as 9 times 8 times 7 factorial, right? And I could keep doing this over and over again. That's going to become essential when we start using the formulas, okay? As far as like canceling factorials, okay? Also, keep in mind that 1 factorial is equal to 1 for obvious reasons, but also realize that 0 factorial is also equal to 1 by definition, okay? So 0 factorial is always equal to 1, not 0, okay? So now, let's move forward. Okay, so now, let's use this in an example. So now, let's say I have 5 people and standing for a photograph, right? And I want to order them up, right? So I want to line them up for a photograph. So order matters in this case, right? So you can only have 1 person in the first position, right? So order matters. So what do? Well, if you think about it, it's just like using the fundamental counting principle that we did before, right? 5. Okay, so now, if I have 5 people, how many different ways can I order them for a photograph? Well, how many people do I have for the first position? 5. And then how many do I have for the second position? Only 4. Because once we choose somebody to be first, they can't be second, right? So that means 4, and then followed by 3, 2, and then of course the last person is last, right? That's only one option. So now the fundamental counting principle says that how many different ways can I pose people or line people up for a photograph? Well, using this, it's going to be 5 times 4 times 3 times 2 times 1. 120 ways, right? Well, or I can use my calculator and just use the factorial key on my calculator. So I can go to math, right? I can go to my math key, and then I can go to probability. And then I can go to the factorial key, which I believe, if you're using a TA83 or 84, it's number 4 on the list. So, and it's going to be a factorial key, okay? So if I wanted to do 5 factorial, I would do 5, and then I would do this step to get the factorial key, and it would put an exclamation point afterwards, and then hit enter. Oops. And it would give me the answer, the same answer, 120. Okay? So the factorial key helps, or the factorial function or operation gives you a much easier way of calculating instead of just typing in 5 times 4 times 3 times 2, or 10 times 8 10 times 9 times 8 times 7, and so on, right? So much easier. So that's the factorial. So now, let's talk in general now about ordered arrangement. So far we've been doing a lot of problems that are considering or using ordered arrangements of distinct objects, okay? The ordered arrangement of distinct objects is called a permutation, okay? So anytime order matters, with distinct objects, it's going to be a permutation. So now there's three things about a permutation. Okay? Now, the formula for a permutation and the symbol is this. So if we have n objects, right? N distinct objects, and we're going to choose k of them. And order matters. So 1, we have n objects. Okay? So we have n distinct objects. 2, we're going to choose k of them. And 3, order matters. Then it's a permutation. Oh, and by the way, oh, we'll get to that. Never mind. So here, so the general formula is this. Well, you know what? I'm going to do this here. So 4 is no repeats. So that's the 4 things. So we have n distinct objects. We're going to choose k of those objects. Order matters. No repeats. Then the number of permutations is going to be this. So in general, it's going to be np k, or yeah, npk. So npk. So the formula is this. This is the general formula. It's going to be n factorial divided by n minus k quantity factorial. Okay? So, for example, in the case of the photograph, where I have 5 people, and I want to see how many different ways can I order all 5 people. Well, in that case, what is k? Well, I have 5 people, that's n is 5, but how many people am I choosing for the photograph? All of them. So in that case, k is equal to n. So that's the special case, right? So what happens to this formula if k is equal to n? Well, what if k is equal to n? Okay? Well, npk just becomes what? Just becomes n factorial over 0 factorial. But remember, what is 0? 0 is equal to 1. 0 factorial is 1. So it just becomes n factorial. So just like in the photograph. So anytime that you want the number of permutations and you're choosing all of them, so that means how many different ways can I order all n objects? It's just a matter of just doing the factorial. That's it. And using the fundamental counting principle. Okay? So now, what about the case where k is less than n? Right? So, in this case, let me even make it more distinct. It's going to be this. So k is at least 1, but less than n. Okay? Well, then it's just this formula. Okay? So it's just going to be using this formula here. So it's just npk. Okay? So again, it's just going to be the formula. Okay? Now the last thing is, well, what if I allow for repeats? Okay? If I allow for repeats, okay, then what happens is this formula just reduces to n to the k. So I have n objects. I'm going to allow for repeats, which means that I'm going to have all n objects to choose from. And how many times am I going to choose them? How many objects do I want to choose? K. So that means it's just going to reduce to n to the k. Okay? So again, for part A and B, we're going to use this formula here for the number of permutations. For C, if you allow for repeats, then it's just n to the k, and that's it. Okay? So now, let's do this. Let's use this and answer some questions now. So let's say we're at a local college. And the local college has a club. And the club is made up of 14 men and 18 women. And so let's suppose that the club is going to elect a president, vice president, and treasurer. Okay? So, we're going to elect 3 different positions, right? 3 distinct categories, right? So we've got president, vice president, and treasurer, right? And it says, what is the probability that the president will be female and the other 2 officers male? Well, how do we figure that one out? Okay, well, we're going to say that the president has to be male, right? And, oh, no, female. The president is going to be female, and the other 2 are going to be male. Okay? So now, we want to find the probability that the president will be female and the other 2 officers male. Well, what do we need to find out for probability? Okay? So let's think about this. We need to find the probability president is going to be a woman. And vice president and treasurer men. Well, what do we need to find out? Well, one, we need to figure out what are all the different possible ways of choosing a president, a vice president, and a treasurer from what? The whole group. Out of how many people do we have here? 32. So we need to first figure out how many different ways can we get a president, vice president, and treasurer out of the whole club of 32 people. Well, does order matter in this case? The answer is yes. Why? Because the first person I choose is going to be one of those spots, right? And once I choose that person, then that person can't be another position, right? Only one position per person, so there's no repeats and order matters. So this is a permutation. So now, to find out all the different possible outcomes, I need to find out how many different ways can I choose what? 3 people out of 32, and order matters. So that means the total number of possible ways is going to be on the bottom, and that's going to be what? 32p3. Okay? Now on the top, well, this is the situation. We want all of the outcomes that give me this. The president is female, and the other 2 positions are male. Well, I have 3 spots to fill, right? Okay. Well, I need to figure out how many different ways can I choose a female for president and choose a male for president and treasurer. Well, if order matters, well, this is all going to be a permutation. How many women do I have to choose from, right? I have 18 women to choose from. Well, how many women am I choosing? 1. Okay, so order matters. So this is going to be, out of the 18 women, I'm going to choose 1. Okay? Now, for the other 2 positions, how many different permutations are there for men to have men as vice president and treasurer? Well, how many positions do I have to choose from? 2. That's how many positions I need to fill. How many men do I get to choose from? 14. So this is going to be 14 P2, right? Now, the fundamental accounting principle, so this is the total number of ways, right? So this is the total number of ways of choosing one man, one woman for president, but order matters. This is the total number of ways of choosing 2 men to be vice president and treasurer when order matters, okay? And no repeats, right? So these are permutations, right? So now, this is the total number of ways to choose 1 woman. This is the total number of ways to choose 2 men. And what are we going to do with those 2 numbers? Multiply them together. And that's going to give me the total number of ways of getting this. Okay? So now I have my 2 numbers and I'm just going to multiply, right? So all I have to do is use my calculator to figure out what these numbers are using a certain function that I'm going to talk about. Okay? But let's just use the definition, right? So, how many different ways? So let's just figure this out. So P18(1), right? So N and K. So this is going to be 18 factorial divided by what? 18 minus 1 factorial. Well, what's this equal to? This is going to be 18 factorial over what? 17 factorial. Well, what does this reduce to? Well, let me rewrite the numerator. I can rewrite the numerator as 18 times